Another way we can do this is to heapify directly, that is, to put those numbers directly in a heap. So the time complexity of this will be big O of n. Now here, I will introduce you what heapify means. First, to heapify is to turn the numbers array above into a binary tree, and after we turn them into a binary tree, we are going to figure out a way to turn it in a minimal heap. We have something important to remember when we heapify, that is, we must compare each node to its child node, and if the right condition is not met, we are going to exchange it with its child node. So in this binary tree, if you look at the lowest layer, we see they are all leaf nodes and don't have any children, so we don't have to worry about the lowest layer on the layer before, because all of them is the leaf nodes. First, let's consider this turn. What we want to do is to convert it into a minimal heap. 10 is larger than both its children, so what we are going to do is to exchange it with the smallest child. When we exchange it with the smallest child, 10 is now in the correct position. Now we can consider another node on the same level. Now we can see 9 is larger than 6 and 4, so all we have to do is to exchange 9 with its smallest child. This time 9 is in the correct place. Now we can move to the level above. Let's look at the nodes in it. Here, the 12 is larger than both of its children, so what should we do? Now all we have to do is to take 12 and swap it with its smallest child node, and after we exchange the 12 and its smallest child, now when you look at this 12, it's still larger than its two children, so what should we do? All we have to do is exchange it with the smallest child node again, and when this exchange is done, let's look at the current binary tree. Now we can see it is a complete binary tree, and at the same time it satisfies the property of a mean heap. So how does this have a time complexity of big O of n? The n here is the number of nodes in this binary tree, and if we are going to calculate the time complexity of this operation on a binary tree, you will see that the time complexity is the number of times we swap nodes. If we look at the bottommost level at height 0, the number of nodes you should have is n over 2. At most, it's half of n. So how many times can we swap nodes? Because they are all leaf nodes and there aren't any child nodes, right? So the max number of exchanges is 0, because it doesn't have to exchange with any children, right? Then, for the level above the leaf layer on this layer of height 1, the maximum number of nodes in this layer is half of the n over 2 nodes left. Is that right? Now, it's n divided by 2 squared for the number of swap it can make. So each node can only swap with its smallest child once, so the number of exchanges is 1, and the time complexity of this layer is the number of its nodes multiplied by the maximum number of swap it can make. When we are on the level at height 2, how many nodes are on this level? Its remaining number of nodes halved again, so it's n over 2 cubic, isn't it? And the maximum number of exchanges is it can exchange with the next layer and then swap again with the leaf node layer. So the maximum number of swaps is 2. So just by using these three expressions, we can work out an equation. Well, when the height is I, the time complexity of each layer should be n over 2 to the power of I plus 1. So the whole thing is multiplied by I, which is the time complexity correlated to a layer at height I. So if we want to find the time complexity of the heap of I operations, what we should do is sum up all of the time complexity of each layer. What equation should we get? We start with I equal to 0 to the maximum of I equal to its height log of 2n, and if we write the expression for each layer, then we can get the expression of total time complexity. Then we can extract this n and convert it into an expression like this. And we can also extract this half. So to get this equation, now we left just the expression for our sum. And next, we can expand the sum like this. And we can see that this sum in this equation is an arithmetical geometric sequence. Well, the first term is 0, its difference is 1, and its common ratio is a half, and n is how many elements we have. So as n approaches infinity, this sum converges to 2. So if we rewrite this equation and put converged value here, in the end what we get the value which is converges to n. By replacing the sum in this equation with its converged value 2, we can get the expression is n multiplied by 2, which is simplifies to 2n. So the time complexity is therefore O of n, as the constant factor 2 doesn't affect the order of the complexity. Yes, it converges to 2 as n approaches infinity is a key factor that makes it O of n time complexity for constructing a heap by using the bottom-up approach, which is more efficient than top-down approach with the time complexity of O of n log of n.